Welcome everyone, my name is David Broman, and today I'm going to teach you a little bit about the lambda calculus and about type checking and how it relates to the lambda calculus. So if you haven't heard about it, I hope that I will give you a gentle introduction. I will show you some derivation, some formalization, and also some examples in OCaml. So let's start with a brief history of the lambda calculus. So the whole theory dates back in the 1930s. But today, it's actually used in many languages, both in functional languages, but it's also incorporated in many object-oriented languages today. If you look at functional languages, you have Haskell, for example, or standard ML. And standard ML was actually designed to be able to create this theorem provers called LCF. We have Lisp dating back in the 60s. So all these are programming languages and related things. But the theory dated back actually in the 1930s, and this is Alonzo Church, who invented the lambda calculus. And another very important person here is Alan Turing, who invented the Turing machine. It was mainly used for formalization about computability, and they also proved the equivalence between, for example, the lambda calculus, the Turing machine, and also Gödel's general recursive functions. From the beginning, it was about computability, but today it's used a lot in the foundation in programming language research and then also in modern programming languages. To think about the lambda calculus, we need to talk about syntax and semantics. And if you haven't looked at my previous videos about compilers where I introduced these concepts, the idea is that the syntax is describing the structure of the program, whereas the semantics describe the meaning. And here we have some lambdas described in some concrete syntax. So this is what you can see in many different programming languages. So this is more like a scheme style, a backslash. This is how you write it in Haskell, for example. This is how you write it, for example, in Scala. And this is an example how you write it in OCaml. But abstract syntax is a simpler representation, typically used internally in compilers. And this is often when we talk about the lambda calculus, we just write an abstract syntax, typically defined using BNF syntax. And here we have then the term t, which is the non-terminal. And that is either a free variable, like x here, or we have a lambda abstraction where x is bound inside t here by this lambda. Or we have an application or a function application where we apply this term when it's been validated to a value to this term, which should be then a lambda. And this is basically the whole syntax of the lambda calculus. And just to relate to implementation, if you would implement this in a language, say OCaml, you can create a algebraic data type. For example, here we have the type term, and then three different constructors, like a variable, just a string, a lambda, which is a string, the variable that is bound inside the body here. So this corresponds to this here. This x here corresponds to the string. This t here corresponds to the term here. And then we have the application, which has two terms. So there are two main rules or conversions in the lambda calculus, the alpha conversion and the beta conversion. The key thing here is about a regex, a reducible expression. So this is a lambda here. It's applied to a term, and this is called a regex. So the beta conversion is basically making a functional call. So it takes this function here, which is anonymous. It doesn't have a name, but it's got a variable here or a parameter, and it's applied to t2 here. So what happens then is that the value of t2 is substituted for all occurrences of x inside t1. And this is what we write here. We say that all x are substituted with t2 inside t1. And this transformation is called beta conversion. Another thing is called alpha conversion. And it basically says that if you have some lambda here, where you have an x variable, that is then bound inside the term here, so there could be many x's here. That's the same thing as if you have y and it's bound in the same places. So it basically says that you can freely change the name of the variable as long as you change all the names of the same variable. So these are the two main rules, and this is basically the whole lambda calculus. And with that, we can compute anything that is computable on a machine today. Pretty cool. There are also some conventions to make it easier to write. And one convention is about how do you write an application. And it basically says that it associates to the left. So this function here, or function application, you have a function f, which is applied to x, which is applied to y. So it's actually two arguments. And when you write it in this style, it's actually called curried. So it's curried because you apply two arguments to one function. And this is the same as if you write like this. So you put a parenthesis around the first one. So it means that you first apply x to f, which then returns another function, which you then apply y to. And if you look at it in OCaml or in some other function language, you would just write foo xy. So this way of writing a function application is called juxtaposition. Let's look at another example. Here we have two lambdas inside each other. What are the precedents that would be the correct way of putting out parentheses? So think about this. This is the same convention that is used in basically all functional languages. Before I give you the answer, stop the video and try to think first by yourself, and then I'll show you the answer. All right. So the convention number 2 here is that the bodies of the lambdas extend as far to the right as possible. This means that this expression is the same thing as this. And here we see that body of x is basically then the rest here. And that's what convention 2 says, that it extends as far away as possible to the right. And you see y here, the lambda y, also extends as far as possible. And then we see that y applied to x, you have this parenthesis, and this part here is due to convention 1, which says that you're associated to the left. And if you would write this in OCaml, we'll do that in a moment, you would just write like this: fun x, fun y, y x z. And note how you in OCaml write this arrow syntax, but this is more the standard formalization way of writing using the lambda character. Z here is actually a free variable, because you can see that it's not bound by any lambda. X here is bound by that lambda, y here is bound by that lambda, but Z is not bound by any lambda here. So that means that Z is a free variable in this expression. And we will say here that this is then not a closed term. A closed term does not have any free variables. Now let's look at the lambda calculus, and I will show the simply typed lambda calculus here. But to begin with, we'll not care so much about the types. We just look at the untyped part. So the syntax here shows the abstract syntax, but we often use this abstract syntax with this notation directly when we write out examples. Sometimes we write E, sometimes we write lowercase t, but here I've just used E. So then we have an expression, E, we have X and the body, and then the application, just as I showed before. And we can see here also that we give it a type here. So we give that X, the variable here, has this type, capital T. We'll not use capital T here or the types in the evaluation right now, but I will explain that in a moment. This is called by value semantics that I will show. That's why we need to define what is a value. And in this simply typed lambda calculus, only one thing is a value, that is the lambda. Lambdas are high order, so they can be passed around freely as values. Then we have the types, so we'll come back to that, but the only type we have in a simply typed lambda calculus is the arrow type, so the function type. That should be familiar to you if you are familiar with the functional programming. If you have not taken my tutorial in OCaml, I think that's a good idea, because it's a little bit hard to understand the simply typed lambda calculus without really understanding a functional programming language. And then we have the last part, and that's called the environment. This gamma here is the environment. And it's basically, you can see it as a cons list. It's either empty, so there is no environment, or you take the current environment and then add to one element which says that this variable is associated with this type. And then you can see the recursive definition. So if you're thinking about this as a cons list, this is the empty list, and this is the cons element, where this part is the element and this is the rest of the list. So it's kind of written in the backward order. Now I'm showing the syntax that is common in PL papers, so programming language papers. If you want to learn to read some research papers, it's good to understand this notation. That was the syntax. let's look at the semantics. And first off, we were going to look at the dynamic semantics, the evaluation rules. And what I show now is a small step operational semantics. It's also possible to define a big step operational semantics, but that I might talk about in another video. If we look at the rules for the small step operational semantics or the evaluation, we have a few rules, and these are defined with the following relationship. So this relation here, this big long arrow, basically says that E, an expression, is evaluated in one step into E prime. And the small step operational semantics says that you take steps. So you take small steps, you evaluate the expression step by step until you end up with a final result. So this is a so-called inference rule, and it's written with this bar. And you can read it like this, going in the clock order here. At the bottom here, we have the conclusion. But for this conclusion to hold, you need to have that the premises are holding. And the premises are on top. We have an application here with two expressions or two terms, E1 and E2. And then it evaluates E1 one step. So it takes one step for E1. So we get E1 prime. And then we return the application again, where we have evaluated the first term or expression here, E1 prime. The second rule of this small step called by value operation semantics says that, okay, given that this one is already a value, so we have applied this rule many times until we get a value here, and the only value we can have here is the lambda, so this is the lambda. That means that this is basically the lambda. Then we evaluate this one, E2, so that it takes one step. And then we have V1 and an updated E2 prime. These rules are called congruence rules because they go down deeper and deeper into the term. And the last one, which is called a computational rule, is basically the beta conversion or the beta step. That's why it's called E beta. So it says that this to the left is a lambda, so it's a value, and this V2 is also a value. If that is true, we are substituting V2 into all places where X exists inside E1, and that is the beta reduction. So these three rules define the whole lambda calculus here. Let's look at an example, just to understand what is going on here. Here we have a lambda x, so that's the variable name, and then the body, we say that x plus 1. And look here now that we have plus, so we say that we have some other operators, like plus and minus and so on, and we'll use that in the examples here, even if we have actually not defined it in these rules. So if we would be very formal, we would add this to the syntax, plus and also integer numbers here and types for integers. We would add that here and also add rules for that. But we'll not do that. We just assume that they exist because it's fairly easy to understand what they mean. Okay, so we want to evaluate this expression. If we take one step, we will reduce into this. So what happened? Well, the first step would be that we have this lambda here. Which rule applies? Well, this rule cannot apply because this assumes that V2 is a value, but 2 plus 3 is not a value. This rule, would it apply? It says that E1 would take a step, but E1 cannot take a step because it's already a value. So it must be this rule. And here we see that V1 is a value, which is true, it's the lambda, and then it should take one step on E2. So what should happen now? We probably think that now we should apply this 5 to this lambda. So we get this result. So what happened was that this 5 was applied and it was substituted. So this 5 got into this x here, and then we have 5 plus 1. And since we applied the lambda, we got rid of the actual lambda. So we just have 5 plus 1 left. And this is exactly why this rule applies here. So it's the beta reduction. And then, of course, the last step is that we compute. We get value 6. So this expression would look like this in OCaml. So here you can see that lambda here is written with fun. The x here is the same as the parameter here. We can also see that we write arrow here in OCaml. This is the same as the dot, so that we separate the parameter from the body of the lambda. And here you have x plus 1, and then you have the argument. So let's write this in OCaml. And we just use this REPL here. So we can write fun x plus 1, and then 2 plus 3. And we compute and get the value 6. Let's take another example. A little bit more complicated one where we have a y, lambda y, and inside that we have another lambda. And we see here that you have the parentheses around here. So this whole expression here is applied to this value here, which is also lambda. And then we are using currying, so we have 2 arguments here. Then comes number 4. The first thing that happens is that we will evaluate this substitution here. So this lambda here will be substituted for every occurrences of y inside here. So here we see the result. We took this value, this lambda here, and substituted for y. So that's why this landed here. And since we applied to this lambda, the lambda y disappeared, and we have this expression left. You can pause the video now and just make sure that you understood this step. The next step is that we apply this number 4 to this lambda. And now we have this expression here, and we will apply this 4 to this function, which means that we get 4 minus 3, and then we just compute, and we get in the end 3. So let's look at what it looks like in OCaml. We would write like fun y, fun x. This would be the 2 lambdas. Then inside here, we have the body here, and then have the argument, this one, and then 4. We can just write this in the REPL and see what happens. So fun again. So we have the 2 lambdas here. Y is applied to x plus 2. And then we have the first argument, which is again a function with parameter z minus 3. And then the last argument is 4. And if we run this, we get an evaluation that ends up with value 3. So I hope you understand now the basic idea about the evaluation rules. So this is the dynamic semantics of the lambda calculus, where you can do some computations. Now let's look at types and type checking. When we write like this, it says that a term t has a type capital T. Note that we sometimes write lowercase t and sometimes write e for expression. It's the same thing. Another way of saying this is that term t belongs to type t. Then we have the definition of well-typedness. We say that a term t is well-typed if there is some type, capital T, such that t has a type t. Lots of t's here. So this means that it's well-typed. It means that it's good, it works. How do we figure out if it's well-typed? Well, we have a type checker that checks that. A type checker basically says, given a term t, return the type capital T that t belongs to, or return an error. So it means that either it is an error or it's well-typed. That is what's happening when you type check a program. We can do static type checking. So that is performed at compile time. It's typically proven to terminate. So you want the type checker to not take forever. And it's conservative. But all languages are not statically typed. And everything cannot always be statically typed in a real language. And then we have instead dynamic type checking, which is taking place at runtime. For example, array bound checking that is done in, for example, Java or Haskell or OCaml, checks if you're accessing outside the array, you get an exception back instead of a program that crashes. So you check this at runtime instead. Or you have languages like Python or PHP, which is basically dynamically typed languages where everything is checked dynamically. So we have the concept of getting stuck that we don't want to do. To be able to talk about getting stuck, we first need to introduce the definition of normal forms. So a term t is in normal form, we say, if no evaluation can be applied. So that means that if no inference rule applies, we are in normal form. So to say it a little bit more formally, that is, no t prime exists such that t can be taken a step to t prime. So we can basically not take any more steps in the small step operational semantics. Then we are in normal form. If we have then a term that is closed, and if you just remember what we said about closed terms is that there are no free variables, then we say that it's stuck. And what we want to make sure is that we cannot get stuck. So how can we figure that out? can we figure out if we cannot get stuck without actually evaluating the term? I mean, it's simple to just run it and see if we get stuck or not, but that is typically not always what we want. So can we do that? Can we check if it's going to get stuck or not without evaluating it? And the answer is yes. And that is, again, the type checking that we talked about. So we need to introduce a type system. We need to implement a type checker. And if we are doing this formally, we also want to prove that the language is sound, but that we can never get stuck. There is a slogan saying that a well-typed term cannot get stuck. And this is basically what we mean by a sound type checker. So now let's look at the simply typed lambda calculus again. We have the syntax, we have the semantics, the dynamic semantics, and then we have also the type system, which is given also by type rules, which are inference rules. So this is the type system. And the relationship is typically written like this. It's a triple where we have the environment. This was the environment over here. This is just a symbol that is used to separate the different terms. Then we have E, which is the expression or the term. And then we have the type. So it says that this expression, this term, belongs to type T or is well typed given the environment gamma over here. So we have three rules. We have, first of all, a rule saying something about a variable. If we have a variable x here and we have an environment gamma here, if the premise holds that we have an x with type T in this gamma, then we know that this type is T. So we read it like this. That's the T-var rule. Another rule is this one. So it says that if we have a lambda here with the environment gamma, now if we go inside the lambda, we extend the environment to also include x here with type T1. In that case, E2 should have type T2. So we get this T2 by looking at the premise. And we have T2, we know that the type of this whole lambda will be an arrow type going from T1, which is the type of the parameter, to T2, which is the type of the body. And this is the type rule for a lambda abstraction. And finally, we have the type rule for a application. And it says that E1 has to have an arrow type. So we see here that E1 must hold that E1 is a arrow type from T11 to T12. And then we can see in such a case, T12 is the return type, which kind of makes sense because we applied E2 to E1. There's another requirement here that E2, which is the argument, needs to have type T11. And T11, you can see that T11 exists both here and there. So it means that the type of the argument here must have the same type as the parameter's type, which makes sense as well, right? So if you apply something to a function, the type of the argument needs to have the same type as the parameter. So this is basically what this TApp rule says. All right, so this is the whole simple type lambda calculus. Now let's look at some examples to just figure out how they actually work. I will now show you the exercise, and after that, I would recommend that you pause the video and try it out yourself, and then listen to my answer afterwards. So the following term here, this one, lambda with a body x, and then it's applied to a value true. Is the term well typed? Remember the definition. And if it is well typed, what is then the type of this whole expression here? And note now that we have introduced basic values like booleans here, true and false, and the type boolean, and we'll also use integers. They are not here as before, and it's pretty straightforward to just define these type rules and the syntax for booleans and integers. So try to see if you can figure this out. All right. What we want to do now to check this is called a typing derivation, which is basically creating a tree from this expression using these type rules, and then we'll see if it type checks. And this is actually how a type checker is implemented. It creates this, recursively goes through and uses these rules and creates a tree. So let's look at the example here. And we see here that this expression and this expression are the same. We assume that this term was closed. And we can then just assume that we have an empty environment here. Which rule applies here? Well, we see here that there is an application. That means that the tapp rule must apply. We can start by looking at it true. True is Boolean. So we look at this rule and it is true. So let's see if this part holds. So what we do now is that we're going as before clockwise, and we write out this part here, gamma E1, in this case, it's this whole thing here, right? Then the question is, how do we type check this? Which rule applies? Well, it's tabs because of the lambda. So we go to this rule, and then we write out this part here. You see E2, so we'll extract out E2, but then add these things to the environment. So let's do that. We have now that X here, which was the body, and then in the environment, we have X is bool, which means directly we can say that this means that we have a variable. We are actually applying this rule right now. So if this is a bool, then we go back to these tabs, and we should fill in T1 and T2. So T1 was this one. T2 is the type that we returned, which is bool. So then we get that the type of this whole thing, which type checks, is bool to bool, which makes sense. This is a lambda, and we have then an arrow type. And if this is a bool to bool, this rule here, this premise holds, which means then return T12 here, and in this real case, T12 is bool, so we return a bool. And this is the typing derivation, the tree, for this expression. So the answer is, it is well typed because everything was correct according to the rules here. And the type of this expression here is bool, and that is what we can read out here. So to make it concrete, in OCaml, we will write like this, fun x colon bool. So we have lowercase letters here in OCaml, arrow x, and then the true. And let's try to type that in. Write fun x bool, arrow x, and true. And we see here that we evaluate this, and also as the response here, you can always see which is the type of the whole term, and it says that it is bool, which is also the same conclusion as we had here when we did the manual type derivation. And if you just look at this now, it's kind of obvious, right? We have this true here, which is Boolean, which is correct because this parameter is also Boolean. So since x is a Boolean, x here must be a Boolean, and then the return type of the whole expression is a Boolean. So we can look at this expression and do this derivation more or less directly, especially for these simpler expressions. So let's look at another example, and it's a little bit more tricky, but it's not too hard. So here we see that we have an environment here. So we say from the beginning that, okay, we have some environment where we have a variable y, which is an integer. And then we have a lambda here, where we see that we have the parameter x, which has type bool, and the body is a function application where we apply some x here, which is the parameter, to y, and y exists somewhere else in the environment here. And we apply false here to this whole lambda. Pause the video and see if you can figure out if this is a well-typed term or not. And if it's a well-typed term, try to figure out what is the type. And if it's not well-typed, see where would the type error be. All right, so let's build the type tree again, and then we'll see that we can actually see this more or less directly. We have the term again here, and here we see the typing environment. What is the first rule that applies? Well, we have an application, so it must be tapp. We can first look at false here. False is bool, so that works. Now the question is this a function type, and is the parameter a Boolean? We take, as we did before here, E1 here, and check this E1. So E1 in this case is this whole lambda, so we write that out here. Now we're checking this lambda, and which rule applies? Well, again, tabs, and tabs checks that the body is this y applied to x is the body of this lambda. So we write that. So we have this premise here corresponds to this here. Well, how do we check that? Well, now we see that we have an application. So now we have to go to the next rule, and it must be the T app. So we use T app again. So we're building the tree, and we can check first y here. So we say y, and we look at the environment, and then we say, what is the type of y? Well, which rule applies now? Well, it must be T-var, since we are checking y. So it says y here. And then we see here, does y exist in the environment? Yes, it does. And it's got type int. Hence, we have the conclusion here that this whole thing must be a int. So this is the conclusion. This T here corresponds to this. All right, so y is an integer, but is that really correct? No, here we got some problem, right? We see here that we had this T app here, and we want to conclude that E1, this one, is an arrow type, which makes sense because we're applying something to it, so it should in the end be a lambda. But it's not. It's an integer. So it's an integer, but it should be an arrow type. Hence, there is a type error. So we got a type error. So we couldn't finish this whole type derivation. And therefore, it's not well typed. We have a type error in this place. And if we could actually probably have seen this directly. And this, when you're analyzing a term, you can basically just look at the term and see if it makes sense. This is what you do when you're programming in a functional language. So here you see that false applied to this Boolean here, which was correct, right? So false is a bool, and the parameter is bool. X here is then a bool. Y here, we get from the environment, is an int, but you cannot apply an bool to int because y here must be a function, right? So it must be of a function type, which it was not, and that's why you have a type error. We can check this also in OCaml just to see as a concrete example. The trick here is that we need to, in some way, encode that we have an environment. And we can do that by basically just putting the lambda. So we have this lambda here, over here, yx, you see it here, and the whole expression with the false. We put this whole thing in a let expression. By doing that, we define the environment. So we define here that y, and I just arbitrarily picked the value here, saying y is equal to 10. So it means that we have something called y, which is an integer, which corresponds to this. And then we'll see if the type checker discovers that this is an error. So let's see what happens if we enter that in the REPL. So we write let y equals 10 in parentheses, function bool yx, and then false. And we can see here that we have a type error. And the error is over here, underlined with a red underline y here. This expression has type int, which we know because y is defined in the environment, and it's an integer because y equals 10 is an integer. And it says that y has to be a function. It cannot be applied. So it is not of a type arrow type, which was exactly what we saw when we derived it by hand. So this was my last thing about the type lambda calculus with some examples. I hope you understood some parts here. Please tell me in the comments if you understood this or if you want some more examples to make it clearer. Thank you for listening. If you like this video, please subscribe and add a comment and tell me more about what you want to learn about compilers and programming languages.